What is welding? Welding is a manufacturing process used to join metal components by melting and solidifying them. It is widely used in industries such as construction and automotive manufacturing. After knowing what is welding, we had to know what is effect of this on the steel. However, the heat from welding creates thermal cycles that can change the steel's microstructure and affects its properties. We started with mild steel, comparing standard sample against those joined by fusion welding. Based on the graph on this picture, we can see the three key areas for study: the fusion zone, the heat-affected zone, and the base metal. Depending on the cooling rate and composition of the steel, different microstructures such as ferrite, pearlite, bainite, and martensite can form. This structure directly affect the hardness, strength, and brittleness of the material.
To alter the steel's properties, we applied three conditions: air cooling for stability, water quenching for rapid hardening, and tempering at 495 degrees Celsius to relieve internal stress. After polishing and etching the cross-sections, the microscope revealed the shift. Slow cooling produced soft ferrite and pearlite, while quenching transformed the weld into hard, brittle martensite. Using Vickers microhardness testing and ANOVA statistical analysis, we mapped the data. We found steep hardness spikes in quenched welds, whereas tempering successfully smoothened those gradients.
For our results and discussion,
First table is the statistical comparison of hardness profiles across sample regions based on the p-values. This table shows whether the hardness variation across the weld region is statistically significant using ANOVA.
In this case, welded samples 1A, 2B, and 3B mostly show significant differences, meaning hardness changes across the weld are real and not random. Unwelded samples 1B, 2A, and 3A show no significant difference, meaning hardness is more uniform. In summary, this confirms that welding alters hardness distribution even under the same heat treatment. In short, welding plus heat treatment is equals to major microstructural and hardness changes. In this first figure, the microstructure of air-cooled mild steel W1A at 100x and N1A at 50x. This shows ferrite, the light one, pearlite, the dark, and some martensite in the weld. This mixture explains moderate hardness with localized hard spots.
For this figure 2, the microstructure of air-cooled mild steel, sample 1B. 1B at 100x and N1B at 50x. Welded region has refined grains and some martensite, while non-welded is mostly ferrite and pearlite. In short, welding refines microstructure, it increases hardness locally.
This figure 3 shows the microstructure of water-quenched mild steel, sample 2A. This is W2A and N2A. Weld zone shows needle-like martensite, while non-welded shows ferrite plus pearlite. This highlights that fast cooling is equals to martensite formation is equals to higher hardness. In this figure 4, the microstructure of water-quenched mild steel, sample 2B. This is W2B and N2B. Weld region is dominated by martensite, making it very hard but brittle. In summary, weld zone is equals to hard but brittle, base metal is equals to softer and ductile. In this figure 5, the microstructure of water-quenched then tempered mild steel, the sample 3A. This is W3A and this is N3A. Tempering reduces martensite and increases ferrite and pearlite. In summary, the tempering softens the structure and improves toughness.
For the figure 8, air-cooled sample 1A, this shows the hardness is highest at weld then decreases outward. This is due to the heat-affected zone or HAZ. For the figure 9, air-cooled sample 1B, this shows the irregular hardness trend due to non-uniform cooling and microstructure. And for the figure 10, air-cooled mean hardness profile. This shows the general trend or gradual decreases from weld outward. This matches the ferrite and pearlite dominance. For the figure 11, water quench sample 1A, this shows the sharp drop in hardness from weld. For the figure 12, water quench sample 2B, This shows the highest hardness recorded at weld, 168 HB. This shows a strong evidence of martensitic hardening. For the figure 13, water quench mean hardness profile. This shows a very steep drop from weld to HAZ. This shows the extreme effect of rapid cooling. For the figure 14, water quench then tempered sample 1A. This shows a irregular but generally decreasing hardness. This is due to inconsistent tempering response. For the figure 15, this shows a smooth and uniform decrease. This indicates effective tempering and uniform microstructure. For the last figure, water quench then tempered mean hardness profile. This is explain a clear gradual decrease from weld outward. A tempering reduces hardness gradient and improves stability.
The mechanical properties of a weld are primarily determined by the cooling rate, which dictates the metal's internal structure. Rapid cooling via water quenching creates hard, brittle martensite, while slow air cooling produces a softer, stable perlite mix. This speed difference often results in a sharp hardness cliff between the welded center and the heat-affected zone. Percoursed grains lead to a loss of strength. To ensure structural safety, post-weld tempering is used to stabilize the metal. This process relieves internal stress and smooths out hardness spikes, creating a more gradual linear transition from the center to the edges. Ultimately, while quenching provides strength, tempering is essential to provide toughness and reliability needed to prevent brittle fractures in industrial application.
Microstructural analysis and hardness profiling of welded parts. Group 5.